related activities. Within this presentation, I would like to share with you some use cases of those technologies applied into the full railway stack. In fact, we can say that nowadays the IoT is embracing, the digital transformation is embracing the full railway stack in terms of operational services, infrastructure, and also what concerns the part of the traffic management, signals, and their relative supply chains. Basically, let's say that the IoT is providing a new paradigm in order to have enough management and also the part of diagnostics that is made and function of not just the subject mode of act related to the maintenance and engineers, but also is a new paradigm that is providing repeatability, that is providing traceability, and is able to then utilize and reproduce the knowledge that has been acquired. The presentation, within the presentation, we will talk about, we will show actually some real use cases about the predictive maintenance applied to rolling stock, predictive maintenance applied to railway bridges, so also infrastructure, predictive maintenance of track circuits, and last but not least, also application of artificial intelligence and video analytics applied to video surveillance on board the train and also in the station. No matter which kind of asset we would like to manage through an IoT framework, are important 4 pillars to be taken into account. The first one is how to connect the data. So it's important to identify a way to connect different data sources that often they are speaking different languages. They are providing data that are separate with different frequencies. So it's very important often to have an edge device in order to perform agent for computing, in order to also identify the anomalies and also to collect those data to bring those to the center, to the cloud. Then it's important the part of transformation, because the raw data are not enough to extract value. So we need to normalize those data, we need to clean those data, we need to perform ETL activities like extract, transform, and load. So basically we need to reach and blend those data in order to build statistically representative data sets or data lake in function of the size of the data that we are going to manage. Then it's very important to the phase of analysis, because once the database is statistically represented, it's important to then apply artificial intelligence, machine learning, and neural network, deep learning, and other techniques that could allow us to transform raw data into meaningful information. So in order to identify hidden patterns, in order to identify also insights that could be utilized. Then there is the last pillar, that is, let's say, workflow and data visualization, because once that I achieve an information that will be helpful to reduce my cost or to increase the availability of my system, I need them to act accordingly in order to take advantages of this information. So basically, workflow and automatic workflow is fundamental in order to increase reliability, availability, reduce cost, and cost not just CAPEX, but also OPEX related to operational cost, maintenance cost, and equipment cost. So that is a really brief introduction to how we apply the IoT architecture and framework in order to manage and predict processes within the railway engineering. Let's try to go ahead and to apply those into real use cases. For now, let's start with the railway operation. So, how to perform predictive maintenance of rolling stocks. In this case, it's a really simple case that I will show to you all. We utilize the Hitachi solution called the Pentao platform in order to calibrate and validate a recurrent neural network called long short-term memory in order to predict in 20 minutes in advance the temperature of the rotor. This is just a use case. Let's say that from an engineering perspective, it's not the most complex thing that we can do, but it's something that we can show in order to explain how we can connect to raw data and then apply analytics. We have a video right now. So basically what we did, we utilized electric engine in a test bench, so that we were able to collect data sampled like we can see right now. Once that we built a statistically representative data set, we were deciding which variable we want to calibrate to predict. So then we utilized the recurrent neural network, long short-term memory, that is able also to track the seasonability of the data that is analyzed. We then we did our operation of ETL to clean the sample. We utilized a Python script with the long short-term memory taken by a common library called Keras, so something that is also available in the network on the web. And then we did the model training. So the model has been calibrated, so the parameters were able now to predict the temperature of the rotor in function to the frequency of the rotor and other electrical variables. Once that the model was ready to be applied, we tested it, and the results are shown in this slide. As we can see on the left, the evolution of the root mean square is decreasing very sensitively in function of the iteration of the model. So there is a kind of hyperbolic law that is decreasing the value of the error. On the right, you can see actually in red time series regarding the sensor data that have been collected to train the model, so to calibrate the parameters. On blue, there are data collected that were utilized to test the model. And in red, in black, we can see the prediction of our predictive model, of our long short-term memory. As is possible to see, there are no big differences between the blue values and the black values. It means that the model found this convergence, and that the predictions were really effective. But for what concerns the predictive maintenance of rolling stock, not just calibrating complex neural network is the right way to act. Also, that exploration could be utilized, and prescriptive analytics in order to utilize a huge amount of data that have been collected during, for instance, 1 year, and then it is possible to apply descriptive analytics ex post in order to understand what happened. In this case, for instance, we have two trains that were part of the same fleet that were presenting in the line same patterns in terms of diagnostic events and distribution of diagnostic signals. Basically, what we try to do is to utilize the diagnostic event as a dependent variable and the distribution of diagnostic signals as independent variables. And so to find a mathematical law that can tell us when there are some distribution of the independent variable, which are the results of the independent variable. So in that case, we were able to normalize the data to identify weak signals and outliers, and those will allow us to act a data-driven approach to the maintenance of the rolling stocks. Let's switch from rolling stock to infrastructure. So in this case, let's talk about the predictive maintenance of railway bridges. We all know what happened in Genova almost 1 year ago. We all know that the civil infrastructure that were built at the beginning of last century now are facing problems related to the mechanical parameters, the mechanical resistance, because now the loads, the dynamic loads that are crossing those bridges are different with the ones that were utilized in the phase of the project. Also, the border conditions are changing. There are also problems related to weather conditions that are affecting, for instance, the bridges. So basically, it is important to utilize IoT in order to switch from a discontinuous way to monitor these bridges. But for instance, in Italy, we are a cycle of diagnostic trains running on the line, like Diamante, like Ayace, and so on and so forth. But through the IoT, we could be able to switch from this discontinuous paradigm to a continuous monitoring of characteristics of mechanical characteristics of the bridge. For instance, stiffness, for instance, mass, inertial force, and so on and so forth. So in this way, we are able, according to this framework that we are proposing, we are thinking to utilize the commercial fleet of trains installing string gauges on the bogies and on the wagon, in order that once that a bridge is loaded, we can see better the mathematical formulation from this slide, when we can consider that the train crossing a bridge is like a moving force over a beam. We can consider this beam working according to the differential equation of Euler-Bernoulli in the assumption of small deformation. If we also consider the validity of the Hooke law and the Navier hypothesis and the theorem of the Saint-Bernard, we can then simulate how this bridge will react in function of dynamic load that is stressing the bridge. If we consider that the massive motion, that in this case is the axial, is relatively small in comparison with the full mass of the bridge, we then can neglect to consider also the inertial effect of the train. If we consider that we are not in presence of damping, and that the beam is considered undeformed and rest when the train is not going through, we can identify which is the equation of motion that can can model this physical phenomenon. In this equation, in the first member, the first term is related to the inertial force. The second term is related to the stiffness of the bridge. The second member, we utilize the Dirac delta in order to simplify the mathematical and physical representation of the concentrated load, considering the concentrated load like distributed load, in order to avoid let's say, specify which is to show which is the equilibrium and the congruency between the part of the bridge and the left and the right of the load. If we would like to consider the bridge, we want to model the bridge, we can consider it as a distribution of elastic beams that have a known mass and a stiffness that is distributed. And also we have to consider that the damping is proportional to the vibrational speed. In that case, we can even consider that the platform that is then sustaining the infrastructure, then railway armament, can be modeled with a distribution, a flexible distribution of springs, of dynamic springs that can then afford, then provide a different stiffness when the train is going through. Let's avoid the boundary condition. Basically, we can see the number of equations to resolve this system of differential equation could reach, in a specific case of 15 wagons and 4 span bridges and 60 axials, up to 154 differential equations. This is the reason why it is required an IoT framework in order to utilize the parallel computation that can then solve this problem, and that can take data coming from the field data, so the bridge and the train, can take data coming from the engineering domain, like DOMS and Geomedia for Italy are the databases where RFI include data regarding the health of the bridges, but also we can take data coming from the traffic management systems, because we have to understand which is the dynamic load that is going through our bridge. So we need to interface with SCC or CTC to understand how many wagons, how many axials, which is the load per each axial, the bracket mass, and so on and so forth. Basically, in this way, through this analysis, it's possible to automatize all this effort, which is very, very impressive in terms of computational requirement. And then we can deploy a predictive maintenance of bridges made data-driven, and so we can identify when there are drifts in the healthy parameters of the bridge, and then we can set up a more a deeper checkup. We did something also regarding the predictive maintenance of track circuits. I will go very fast. We need to blend together data coming from the automatic train control, the track circuit system, exogenous data, and those data are coming from different silos, so it is very hard to act in this way. So an IoT framework can take those data, normalize those data also in terms of frequency of sampling, and then it can be utilized to identify when there are weak signals, when there are data that are drifting from the expected values, and in this way we can really identify, we can really switch from a paradigm of maintenance based on the experience of the single contributor, the single engineer, switching to a more replicable and standardized approach. Last part of my presentation, it will be very let's say, easier with respect to the first part. Basically, predictive maintenance or IoT is not just predictive maintenance or not just something related to the asset management, but in this case, we are looking at the artificial intelligence applied to video analytics. So we are in a train, there is myself on the left and another colleague of mine. We are simulating now a fight in the train, and through the artificial intelligence, the system is able to convert a structured data, like the video, into a structured value that is a trigger, like something is happening. As we can see on the left, now we are simulating just to discuss very heavily, but nothing happened until that we don't start to simulate a fight. So you can see now we are simulating the fight. The system on your left is found an alert. This alert can be through the interface with the TCMS. It's possible to send the information in the video to the driver, but also at the same time it's possible to send this video to the railway police or another on-ground data center. But the most interesting thing is that once that I identify that there is a punk, there is a thief in my train, and I would like to track him or her before that she or he can disappear. So basically what we can do with the solution called multi-perspective search is to start to search by clicking a target in the video and identify this same target from which camera has been passing through while trying to leave the station or trying to leave the train. So basically, taking into account almost 40 different KPIs, the system is able to track the person, the target that we are searching for, and to explain the last slide. To explain to the police also that could also access to a smartphone where the target is going, which was the path that he followed or she followed, and so on. So this is the last slide. If you want to go deeper regarding the physical mathematical theories that we were discussing before, I can suggest these references that have been published on the Ingegneria Ferroviaria, and there are all the information that you could like to read in order to have more details. Thank you so much and for your patience. Thank you.